Let's solve a simple equation. X cubed is equal to 1. What value of x would make this equation work? If you said x equals 1, way to go. 1 cubed is 1, we have found an answer. Now, are there any more answers? Back in part 1, we introduced the fundamental theorem of algebra, which says that a polynomial must have as many roots as its highest power. We can rearrange our equation as x cubed minus 1 is equal to 0 to make it a more obvious polynomial, and since our highest power is 3, this equation must have 3 solutions. There is an algebraic way to find all 3 answers, but it involves perfect cube factoring and the quadratic formula, and takes some work. Instead, let's try to solve the problem visually using the complex plane. Our question in words is what numbers, when multiplied by themselves 3 times, equal 1? Let's think about this problem using the polar form of complex numbers we discussed last time. We can think about 1 in the complex plane as the number with a magnitude of 1 and an angle of 0, or 360. When we multiply numbers in the complex domain, their magnitudes multiply and their angles add. Our result should have a magnitude of 1, and since 1 times 1 times 1 is 1, if we give each of our x's a magnitude of 1, our resulting magnitude will work out to 1. Easy. But what about our angles? We know that when multiplying complex numbers, our angles add, so we need an angle that when added together 3 times gives 0, or 360. 360 seems a little more reasonable, so what's the correct angle here? Since we're dividing 360 into 3 even parts, the right answer here is 360 divided by 3, or 120 degrees. When we put this together with the magnitude of 1, we have a second solution. It's the complex number with a magnitude of 1 and an angle of 120. This answer makes a lot of sense on the complex plane. Multiplying our answer by itself once results in a magnitude of 1 at an angle of 240 degrees, and multiplying by our answer again lands us exactly where we want it to be at a magnitude of 1 and an angle of 360 degrees, also known as the real number 1. This may seem like a strange answer for algebra class, so let's put it back in rectangular form. Our good friend the unit circle can save us some time here. We would like to know the rectangular coordinates of a point on the unit circle at an angle of 120 degrees. According to the unit circle, our answer is minus 1/2 for the real part and root 3 over 2 for the imaginary part. So now that we have an answer in rectangular form, let's try it. If we multiply out our result, we get 1. Pretty cool, right? We were able to solve a tough algebra problem visually using the complex plane, and get the same exact answer we obtained earlier through factoring. Finally, we've only found 2 answers so far, and the fundamental theorem of algebra demands that we have 3. We find our missing answer going the other way around the circle. If we start at minus 120 and multiply our number together 3 times, we also land at the purely real number 1. So our missing answer is negative 1/2 minus root 3 over 2i. So we found all the answers to our problem x cubed is equal to 1, and shown how the complex plane allows us to find these visually. In this case, using complex numbers saved us some time over the algebraic approach, and for more complicated problems, the complex plane becomes even more useful. For example, what if we changed the power in our original problem to 8? That is, x to the power of 8 minus 1 is equal to 0. We could try to factor this, or turn to our complex plane and see that just like our last problem, where we needed to divide the unit circle into 3 equal portions, we need to, in this case, divide our circle into 8 equal portions. So our solutions need to be at 45 degrees, again along the unit circle. All 8 answers, done. Next time, we'll show how imaginary numbers are the missing piece of the puzzle that make algebra complete.